Hello. Hello. There we go. Hello, and welcome to Calculus 1 SICK edition for 2.6 continuity. So this would be application of limits section, and after this section there is going to be one short section eventually, which is next week, unfortunately, and we are ready for exam 1 should you want one. Now, a lot of people are looking at continuity as unbroken line function that you can draw in one shot. That's not all of the story, but it covers most of the cases. So visually, if I have something like this, then we would say f of x is continuous. And if we have something like this, say g of x, we'll say g of x is not continuous or discontinuous. Now, if you ever take advanced calculus, you will learn about functions that you have to draw in pieces, but they form continuous function. It doesn't really break this, it's just more specific, and that's what calculus is. So, what is continuity? Well, we have continuity at the point, we have globally continuous function, we have piecewise continuous function, and all of those are just reflecting what we need as we are going through our application. So this one over here would be called continuous, and this one over here would be not continuous, but it is piecewise continuous, because if you look at each of the pieces is continuous. So we have to be careful what we need, right? Now, in order to define all of these, we have to start with the continuity at a single point, and that one is good for spotting discontinuous functions, and then we upgrade from there. So the first definition would be f of x is continuous at x equals a if, and then we have three rules that we have to check every time. The first one is that f of a must exist. So this is technically your y value. You can't have an open circle, right? If you have open circle at some x, that means there's no y value there. So f of a must exist. No open circles allowed. Number two, limit x goes to a of f of x must exist. Hopefully you remember from previous class, if Romeo and Juliet, right, approach the function from two different sides and they are disjoint, get this, then there is no limit. That would create discontinuity. And three, this is the one that puts everything together. Limit of f of x is equal to f of a. So f of x and f of a is not the same thing, and you can't confuse them. F of x is a function. F of a is a y value. If you need to write that on a side, write that on a side. So f of x is a function which has all y values, and f of a is the particular y value, a number. So if I want to check continuity of y equals x squared plus 3 at x equals to, let's say, 6, I would run I would run through this 3-point calculation. Number 1, we have to compute f of 6, and that's simply 6 squared plus 3, which is 39. So it exists. Right? This is where we put a green check mark. Great. Number 2, limit of x squared plus 3 as x goes to 6. And that one is equal to, well, this is one of the cheap ones, the easy ones. So we can just plug in. No need for algebra or any other witchcraft. So this works out to be 39, and we say exists. And we do a check mark. Boom. And then, number 3, we see that 39 is equal to 39. Same. So, boom. All 3 worked out. Therefore, y equals x squared plus 3 is continuous at x equals 6. We don't know about x equals 5. We don't know about x equals 2. We only know about x equals 6 because that's the calculation we did. So this is continuity at the point, and you have to run these 3 calculations in order to show that the function is continuous at that point. Now, as you're looking at this, you say, well, are there any faster ways? And the answer is yes. We want to figure out some theorems that will help us plow through this faster rather than calculate every single point. There are infinitely many points in every function, so you would have to sit there and calculate infinitely many points every time to come up with global continuity. So, definition on global continuity. If f of x is continuous at every point x equals a, then I said a, then f of x is globally continuous. And as I said, this would be impossible to compute because we can't sit and calculate infinite amount of points. We calculated only one. It took us 2 minutes, and then, infinity times 2 is infinite time. So, are there faster ways? And the answer is yes. Mathematicians over time proved which functions are globally continuous, and they put that into a theorem, and that is the theorem that you will cite every time when you have to use this. So, theorem says following functions are globally continuous, and now we go and just write the list. Number 1, polynomial which spans from constant function like y equals 7 all the way to whatever degree of polynomial, x to the 6, x to the 10, whatever. So p of x equals a0 plus a1x plus a2x squared plus ... plus a n x to the n, whatever we decide to end. Exponential function y equals a times b to the x 3 logarithmic function y equals log base b of x 4 sine x and cosine x. Now your book is going to list the other ones, but they're only continuous on a little part. So we're not going to worry about those in the globally continuous functions because they have vertical asymptotes. Tangent has vertical asymptotes every pi over 2, 3 pi over 2, and so on. So clearly not continuous on the negative infinity to infinity. But it's piecewise continuous. So we'll get there. And number 5, combinations of continuous functions. Now this is a new theorem. It's a separate theorem. So we're going to write it as a separate theorem. Because absolute value of sine x is continuous, absolute value of x is continuous, square root function of x plus 2 is continuous, right? Square root of a polynomial. So the continuous combinations of continuous function, meaning function composition of those functions, is continuous function. So the theorem states that function combinations and function compositions of continuous functions are continuous function. So function combinations and function composition of continuous functions are continuous functions. So those would be f plus g, f minus g, f times g, f divided by g provided g not 0, because that's discontinuous. Let me give you an example immediately, like sine x divided by x squared plus 1. That will be this. Because x squared plus 1 cannot be 0 ever. Any number that you put in square for x squared will always be positive value, and then you add 1. So you can never reach 0. There's no 0 in the denominator. So that would be something like that. Then we have 5 nth root of 7. Absolute value of f of x. If f of x is continuous, absolute value is continuous. So all of these. And then finally, function composition, which is f of g or g of f. That's a function composition. So all of these, if you combine two functions, and these two theorems is how you solve problems. Those of you going to Calc 2, good. Those of you going to Calc 2 will use this when you hit those sections that students usually explode their heads in, because they forget this stuff. Calc 2, there we go. Integral test. Look at that. To solve a calculus 2 problem, you have to show that the function 1 over x squared is continuous. So both 1 and x squared are continuous because they're polynomials. That's the first theorem. And their quotient is continuous because, and then there is the denominator domain 2 to infinity, so the denominator can't be 0. So we are combining, in this particular case, to solve this problem in Calc 2, we are combining knowledge that polynomials are continuous, and then that division when x is different than 0 is continuous. So this is how you solve problems later on. Now, students forget this stuff, so when it's time to do these proofs, they don't know what to do, and it turns out to be a problem. So these are the two theorems that you will be using most of the time to show that the function is globally continuous. And that is what we need in calculus. We need continuity for certain aspects, right, of the course. So now we know how to find globally continuous function. If it's a member of this group combined with another function that is also a member of that group in one of these ways, the overall result is a continuous function. But what happens if it's not continuous, right? Well, in that case, we will have one of the three rules fail at that point that we are observing. So let's draw three graphs. And observe which rule fails, rule 1, rule 2, or rule 3, to make it discontinuous. We will all quickly agree that all three functions that I am drawing right now are discontinuous functions because we see that they are interrupted. So that's that. So clearly here's my A. Here's my A, and here's my A of interest. And now my question is 1, 2, 3, 1, 2, 3, and 1, 2, 3. Which rule fails? The rules are f of A exists, limit of f of x exists, that's if x goes to A. And rule number 3, if those two are the same. I've seen students write 1 is equal to 2, like this as well, whatever. So, which one fails in each of the cases? For the first graph, which one fails? Do we have f of A? What is that black dot? That's your f of A. So it exists. Do we have a limit? Yeah. Left and right reaches the same L. Great. Are those the same values on Y? So 3 is what dies in that case. So it passes first two, and the third one is one that doesn't match. What happens for the second one? What happened? Number 2, very good. There's no limit. There's no limit because it is, as you can see, from the left and from the right, it's a different number, so it fails here. And how about the first one? Number 1 fails because we don't have a dot like this to give us the y value, the f of A. So the first one fails. So this is, these are the 3 ways in which a function fails to be globally continuous if you have, right? So now, if we go back to that bridge problem we talked about somewhere over here, can't remember where it was. Where was the bridge? Oh, there it is. You see that the bridge problem clearly is discontinuous. You do not want to drive on this bridge because it's not a continuous function. And it fails number 3 because the section of the bridge exists, but it's in the water. So that's your f of a. And limit is the same. You can approach from left and right and fix it. And then finally, 3 is what it fails because the limit, which is up there where the orange is, and the section of the bridge, which is in the water, not the same number, not the same y value. So that's how this bridge fails to be continuous. However, many of these functions are piecewise continuous. So on their respective domains, they are piecewise continuous. What can you tell me about y equals 1 over x? It is the graph that you need to be able to graph even if someone shakes you out of bed at 4:30. Oops. So, is this continuous globally? Is it? Is it continuous? Look at it. No. Right? What fails? You name it what fails. Everything fails. This is a function where everything fails. There is no f of a at 0. Right? And there is no limit also at x equals 0. So everything fails. So is 1 over x continuous? The answer is no. 1 over x is not globally continuous. But it is piecewise continuous because there is a piece, from negative infinity to 0. It's continuous everywhere, and there is another piece, 0 to infinity, continuous everywhere. So 1 over x being discontinuous, we don't get to throw it in garbage. Maybe we need just a part. Just like that Calculus 2 problem, which asked what's happening for 1 over x squared on 2 to infinity. Well, y equals 1 over x squared on 2 to infinity is continuous. You say, what? Yeah, it is. Because you draw the graph and you are only considering from 2 to infinity. You're only considering this part of the graph. That part, piece, is continuous. The overall function is discontinuous. Ta-da! Done. So we define continuity at the point. We say that if the function is continuous at every point, it's globally continuous. Then we have those theorems which say the polynomials and all the other ones on the list are continuous. If we combine them, they're still continuous. And then at the end, you have what do you call it? At the end, you have piecewise continuity, meaning that if the function is globally discontinuous, you can find smaller parts of the domain where function is continuous, and maybe that's all you need to consider when you're dealing with. And mainly Calc 2 will be dealing with that when you get into integral test for series. So, well, there will be other parts as well, but for now, that's like the honey pot of where you're going to use this. Bye.